What's going on, guys? My name is Hussein, and this is an overview of how the operating system kernel does socket management using the different data structure, the socket management data structures that is built in at that layer 4 or the network layer, essentially. So I'll talk about what a socket is, what a connection is, and the different kind of queues that are used in order to manage connections and listeners and data that are received for each of these connections. This is a snippet of my Fundamentals of Operating Systems course. If you're interested, check out the pinned comment below. And now let's go to the video. All right, welcome to the nitty-gritty. We'll talk about connections, sockets, and queues. I'll split this into 2 lectures. The first part, we'll talk about in both cases, we'll talk about the core kernel network data structures. But in this particular thing, I'm going to talk about the sockets and connections. And then in the next one, we'll talk about specifically how to read from connections and what kernel data structures does the kernel use to actually implement that. Let's jump into it. This is going to be a beautiful. Let's just swim. You guys here, let's swim. Don't memorize anything. Let's just swim. First concept of a socket. And a socket really, when it comes to actual data structure, is nothing but a struct, really in C. It's also a file descriptor, at least in Linux. In Windows, it becomes an object. Because in Linux, everything is a file. When I listen, and we talked about what is the concept of listening, right? And the fundamentals. So like, hey, I want to accept connections on a specific IP address and a specific port. Hussein, you use the word specific. Can I have more than an IP address in one machine? Of course. In every computer, you have multiple NICs or network interface cards. And not only that, you can technically create unlimited virtual network interface card, each with its own IP address. Ideally, you have a physical network and you have a mapped mount, which have essentially that network virtual IP. Not virtual IP, sorry. It will have a NIC exposed to you that you say, hey, this is my IP address, this is my subnet mask, this is my default gateway, this is my DNS resolver IP address, all of that. This is my proxy, stuff like that. So you can listen on an IP and a port. It has to be those 2 things. So that means I have 4 network cards. I'm listening on the IP address of this network card. You have to specify it. And then you specify the port. And if you've ever built a backend, you'll always see that the default is I don't know, 8888 or 8080, the port, and the IP is the loopback default NIC, which points to myself for development purposes. So that's the TCP/IP 127.0.0.1. That's the IP version 4. For IPv6 loopback, it's bracket : 1. That's the loopback for IPv6. But that's basically the games we're playing here. You might say, I don't have to do anything. When I listen, I just call in Node.js. I could call listen and then I close the bracket. I don't do any of this stuff. Well, this is where we need to talk, you guys. When you listen, you can give the option to listen on interfaces, which is absolutely horrible idea. Horrible. And I'm really mad that this is a default. Apparently, we have to make it a default because it's too much to look up an IP. An IP can changes. And to make it easy, let's listen on all interfaces. And you do that by doing 0.0.0.0 4 zeros, or I think in IPv6, bracket : bracket. That listens on all IPv6 versus all IPv4s interfaces, because you can have both, right? Watch out for this, because you're building a small app that does, I don't know, opens a port and you accidentally deployed it in production, and you wanted like literally to run it locally. And all of a sudden you run it, and it was listen on all production NICs, which happens to one of them happens to be a public IP address or an IP address that is essentially mapped to some load balancer. It's public eventually, right? So now you exposed your app to the public. That's how every single MongoDB instance and Elasticsearch data got breached, because people just listen to all interfaces and deploy it on the cloud. And literally attackers will scan the whole web, scan all the IPv4 ranges, looking for the Elasticsearch MongoDB ports, and then connect and then brute force their way. So that's really dangerous. You really want to listen on a specific port that you actually know. Okay? It's hard. It's difficult. It requires some more work, but it's secure. Now then, we have listened on a port and an IP, Hussein. When you do that, you call a system called listen, and you get back a beautiful file descriptor called socket. And this is, I'm going to coin a name for it, call it listening socket file descriptor. Because a connection is also a socket, but that's kind of a different kind of a socket. It's the same data structure, right? And the kernel kind of stores them in the same file, the same table data structure, but you can see that the socket has only listening socket. It doesn't have like a source IP or destination IP. It doesn't have any of that. But a connection actually is an entity that has two sides. It has source, a client, and a server. So a connection is different than a socket, but I'm going to call it a connection socket. For now, we have a socket. Beautiful. What do we get? We get a file descriptor. Where does it live? It lives in the process ID. Where? PCB. We know all these terms now, guys. We can talk safely with them. So socket is a file. What happens if I fork? Guess what? If you fork, the files are shared, right? Because you get a copy of everything that the process had at that point, including file descriptors. So watch out. Maybe this is by design, and this is good. So when you fork, careful what you forked. You fork, you get everything. So we talked about, let's go back to our single process. We have a single socket in my process. For every listening socket that we create, you guys, we get something called two things. You get two queues. Don't get hung up on the word queue, because they are not actually implemented as a queue, because a queue is it's not very efficient in this particular case. Actually, one of my students called that out. I was saying, like, the queue seems to be very inefficient, but I looked at the source code. It's not a queue at all. It has a hash table, turns out. But we talk about it as a queue because it's easier to talk through it this way. So we get something called a SYN queue, and this belongs to the socket S. And we get another queue called the Accept queue. What are those for? Well, if you're here, you probably know how to establish a TCP connection, right? We do a SYN, and then the server sends back a SYN ACK, and then the client sends back an ACK, and that's called a three-way handshake. And using that, we get a beautiful connection. But that's the handshake. To handle the handshake, we need this sends, which is the synchronization. We use them to synchronize the sequence numbers that we use to label every segment. So that's the first thing, SYN queue. So if you have a lot of listening, you get a lot of SYN queues, essentially. You also get an Accept queue. This stores completed connections. Because if I am a client, I want to connect to you, I first send you a SYN. By just sending you a SYN, I don't have a connection yet. We take your SYN and put it in the SYN queue. We don't have a full-fledged connection. We only have a full-fledged connection if we successfully completed the three-way handshake, right? So then you can see that as I'm putting SYNs here from multiple clients, right? from one client in India, one client in Germany, one client coming from an IP address from Lebanon, one from Bahrain, one. You can see that this can fill up. And then we complete the connection. So we move this stuff to the accept queue and we have full-fledged connection from Germany, from Russia. We have these connections ready. But how many can I keep in my queues before it fills up? There's a size to those, and this size is called the backlog. And you can essentially, when you call listen, you can specify the backlog, and this is actually exposed all the way to the clients. Even in Node.js, you can node and you can specify how much is your backlog. Really pretty cool if you think about it. You might need a large backlog if you have so many connections coming your way and you want to essentially, you're not accepting connections fast enough. We'll talk about accepting in a minute now, because connections that lives here still is not with us, the backend. This is still all kernel. So now let's talk about actually creating connection. Up to here, we don't have a connection yet. We only have a listening socket. That is one file descriptor. Now let's talk about connections. What happened here is like completed connections are placed in the accept queue. We talked about that. After you finish, when you put a SYN, put here, and then the SYN entry comes here until we send back the SYN ACK, and then the client will send back an ACK, and then we match the ACK with the SYN here, and then we remove it from the SYN queue, and we add it to the accept queue. And now we have a full-fledged connection, but it still is not ready. You have to accept it. Who is you? It's a backend application. You must have said, I never called this function in my life. Well, you don't, but Node.js does. Bun does. Django does. All your framework do. Behind the scenes. You must call accept, which creates the file descriptor for that connection. Yes, there is a dedicated files connect descriptor file identifier for each connection. And when you do that, then we create additional 2 queues for the actual data that's gonna be sent. Right? So when you do that, you accept, you're gonna create a connection. That connection is gonna be a file descriptor which lives on whomever the process that called accept. If I am process A, I called accept, then the file descriptor that comes back will live in process A. If I'm process B and happen to have access to the socket somehow, and I called accept, then the file descriptor that gets created will live in my process B's PCB, process control block. And it's going to be a chain of file descriptors. Maybe I'll accept 100 connections. Okay? With everyone, you get 2 queues. Send queue or receive queue. We'll come to that in the next lecture. But each of them, the send queue will go for your outgoing data. So as a server, as a backend, if I send a response to my REST API call, that goes to the send queue. If my client sends a request, it goes to the receive queue. Does that make sense? And vice versa. The client also has a connection on its end as a client, and it will have a send queue and it has a receive queue. The client does not have a socket. It does not have a listening socket. It has just a connection. Okay? So it'll have a send queue and a receive queue. So if a client sends a request, it goes to the send queue, and then eventually the kernel pushes it out to the NIC, and then it holds a receive queue where the response from the server will go into before we actually take the data and push it into the user space and do some stuff with it. Let's go through some animations. So here's my client. Here's my process ID on the backend that is running. And of course, these 2 lives in the kernel, which nothing but a mapped area in the process to the kernel stage, right? So accessing those queues, right, of course, require kernel mode, right, to be accessed. You cannot access them directly from the process. These are forbidden, right? Again, IOUing kind of breaks this rule, but for normal operation, you cannot access them. They are protected. So the SYN comes in here, and it sits in the SYN queue, right? So the SYN will have a from IP address, a from port, a destination IP address, and a destination port. And that's the 4 tuples that uniquely identify this guy. And you put it right here. Beautiful. Now we have a SYN entry. You immediately, as a kernel, reply back by a SYN ACK, where the from and to, from IP and from port is the whatever listening socket IP we listen to, right? And actually whatever the client decided to connect to. Let's say I'm listening on all IPs, right? So the SYN, the client cannot connect to all IPs. It has to specify one. And by knowing that one, that becomes the source IP in this particular case. If and only if there is a matching corresponding socket. Because I drew this as a line, but there's so much stuff going on here. What is going on? If I am doing a SYN and my destination IP is 1.1.1.1, all right, that's Cloudflare's, and the port is 80, then the kernel first looks up the destination IP in certain table that we're going to talk about, and that table says, all right, do I have a matching kernel entry that says I'm listening on this particular socket, on this IP? Yes or no? If yes, let's do it. I accept you. If no, we get an error that no listening socket, or we get an error. All right. So you see, there's a matching that needs to happen. We need to look up. Imagine yourself actually implementing this. How do you do it? There's like billions of ways to do it. A little exaggerating. But the kernel does it a certain way. This lookup should be massively fast. Possibly, hopefully, in the cache, in the CPU, all of these structures really need to be cached, because you don't want to go look up that massive table with all the listeners. You want to quickly look it up. And from this, you would know, based on that entry, you would know which process it belongs to. Absolutely beautiful. So now we send the SYN ACK. Let's say we have a behaving client that replies back with an ACK. Now you have a full-fledged connection. The kernel removes it and adds it to the accept queue. Now we have a free connection here. Now then, the process calls accept, which will copy that connection, creates the content, creates a file descriptor, and copy it to the user's file space. And it will create an entry. Yeah. That says, all right, now we have an actual connection. And it will create the two receive queue, the receive queue and the send queue for that particular connection. Right? Now we have a file descriptor right here. So problems with accepting connections. Let's talk about some problems. Backend doesn't accept fast enough. Clients who don't ACK. And we have a small backlog. If you have a small backlog, you might have a problem with you call accept. By the way, if you call accept and this is empty, you're blocked. And that's why accept is also a candidate for asynchronous IO, which we're going to talk about in another lecture. Beautiful stuff, you guys. Let's talk about socket sharding. There are two different approaches to this, I'll talk about, this is the second one, which is literally getting a different, distinct socket on the same port. So we have two processes that are not talking to each other, yet listening on the same socket. So you have two sockets pointing to the same IP port pair listener, versus the other approach where you have a listening socket and you fork the process to get a copy of the file descriptor, which happen to point to the same logical physical socket. So if those two guys, we're sharing one pair of SYN and accept queue. Here, this is an approach where we're getting two distinct sockets pointing to the same entry. And you do this using the socket option reuse port. Because normally, if you listen on the same port and IP, you get an error, remember? Like socket already listening, that's a common error. But with this, you can actually get to another socket, and you can do it any number of times. Now this poses up, and we'll talk about this now in a minute. Nginx does it, Envoy does it, HA Proxy does it, and essentially what you do is you have the listener and the acceptors and the readers, right? The acceptors, all of these are just different threads or different processes. And this is what's called the socket sharding, where this process will have a socket, and this process will also have a socket, and both represent the same IP port. Now this poses a problem, because if a client came in with a SYN, what do we do in this particular case? Which socket gets the SYN? And now I'm imagining, and I don't know the detail about this, and I'm imagining either you can have two SYNs or one SYN queue for both sockets, but different accept queues for sure, right? So in this particular case, process 1 will have an accept queue, process 2 will have another accept queue for the same port. If I get a SYN on this port, complete the connection, ready, the kernel will do a load balancing. It will throw the accept queue, right? It will throw the first connection on the first accept queue, the second one on the second, the third one on the third, and so on, right? And that's how they do it. So it will distribute the connections on different accept queues, and if it happens to have on this accept queues, this process calls accept on its own socket, which will point to their own accept queue. And in this particular case, we call accept on my socket, which happens to queues. But both are on the same NIC, on the same IP and port. This is a common configuration that people do in order to scale acceptance, right? And this is referred to as socket sharding, or sharding the socket. But the Linux kernel in this particular case does the load balancing. So there is, when they first introduced it, there was a lot of bugs with this, because as connections close and open, we lost the balance of when you have a connection, you're done. The connection is like you have a nice file descriptor to go to. The problem with this is only when you accept connection. The load balancing becomes really interesting as sockets get destroyed and recreated again. Right? All right, let's take an example. Receive buffer this. So receive buffer. So the data comes in, and we know the connection. We know the destination IP, and we know the destination port. The kernel identifies it, right? And you might say, what if I have multiple connections? Well, we use 4 pairs, and this must be unique. The source port and the source IP will give us beautiful uniqueness. So even if the same client establishes 1,000 connections, you're going to get 1,000 different source ports. Even if the IP, the source IP is the same, you're going to get 1,000 different source ports. So you're safe. Right? So the source port changes, the source IP doesn't change, the destination IP doesn't change, the destination port doesn't change. The only thing that changes is the source port. If the same client creates 1,000 connections, you put the data here, nice, and then you acknowledge, right? And you can choose, like as a kernel, you know what, I'm gonna wait a little bit more for more packets to arrive. And then the process calls read, which copies, and that's what I talked about. There's a copy from this kernel to the process. So copy involves going to the processor, because the processor does a read from this memory address, copies to the cache lines, and then from cache line does a write to the new memory location. That's how a copy is. Memory copy is not cheap. It involves going to buses, to different memory addresses. So many copies. And so imagine copying arrays, right? Large arrays. All of this stuff goes through the CPU. right? Again, unless you have like direct memory access from one memory to memory, just copy this stuff, which is also expensive just to set up, as we talked about, right? All right, once you read it, it goes back to the process ID. That's a copy, and we talked about zero copy in general. Like, how do you take this? It depends, like, what do you do, right? If you want to send data from one kernel structure to another kernel structure, you can use zero copy, right? By actually telling the kernel, hey, just, you have these two things, do them, right? But it's very hard to do. Send buffers. The client wants to send something to the server, to the client. Sorry, the server wants to send back, or even the client wants to send. Like, the send buffers exist on both, right? So you send something, goes to the buffer, and it sits here. And that's what the critical part here. When you send something, it doesn't go to the network. Exactly like the page cache. Receive buffer, send buffer, and the send buffer will just not immediately flush it to the network. No. That's a bad idea. We will wait. We will write, accumulate something from the user, more. Then we're going to flush it. And this is where something called Nigel algorithm kicks in. And because, like, hey, a Nigel algorithm actually extend that period. How long do we wait before we flush to the network? So yeah, eventually we send the data. And we get back an ACK. And that's it. Problems with reading and sending. You have clients that does not read fast enough. If the backend doesn't read fast enough, you fill up your receiver queue. If your receiver queue gets filled, the clients slow down. How does this is all determined by something called a flow control. Yeah? Flow control will tell the client, hey, my receive buffer is actually full. Slow down your writes. It's a beautiful, symphony, this whole thing. Summary. So the kernel manages the TCP IP part of networking, at least. Every socket represents a port and IP, right? You can, with a specific socket options, when you listen, you can say, hey, I want to listen on the same port and the same IP, despite someone else is using it. But it's not straightforward. Those two processes have to agree on certain, on certain cookie or certain key to allow them to listen on the same port. And this is basically determined by the first process. If you don't know that key, then you can't listen, because guess what? What stops me from running a process in a server that happened to be listening on port 80, and I do, hey, socket reuse 80. I can hijack packets as a malicious process. That is a bad idea. That was one of the bugs. Early. So to fix that, you need to know what was the key that was used in the listening, and was socket option reuse port actually allowed or not? Can you listen on the same port or not? So it's very, very interesting to learn about all of this stuff. So each connected client gets a connection. We talked about that. And kernel manages all those beautiful data structures, and there is an associated cost to all this, you guys, and it's not very clear from just the listening part, because you don't really shove a lot of data, but for the connection, acceptance, not acceptance per se, but just receiving and actually dealing with packets and parsing those packets. There's so much stuff here that I'm not gonna go through, right? That's a course by itself. That's a book, because you're talking about the actual packets. How do they? And there's, like, when you receive a packet receive data from the NIC, the kernel creates a data structure for it. It's called skip, socket buffers, right? And then adds data to it. And then that there is metadata associated with it as overhead. So the kernel does all sorts of tricks to merge packets together and have list headers, do so much stuff. So you need, if you are like a beefy machine, you need to assign a core or two just for the networking stack, So all right, I'm gonna leave one core or two just for the kernel to do all this complex networking stuff. especially if you have like a beefy CPU.